Hello everyone. In this lecture, I will focus on implementation of Boolean expression or Boolean function using PAL, which is nothing but Programmable Array Logic. And I have already told you, if it is PAL, that means it can be assumed as programmable and, because PA is there, so it is combination of programmable and plus or followed by fixed or, right? That means and operator here will be programmable and or operator here will be fixed. So let me solve example for that so that it will be clear how to implement any Boolean function or expression using PAL. So the question here is like this: implement the following Boolean expression using PAL, that is Programmable Array Logic, right? So function f1 is abcd. Okay, let me write it in capital. So suppose it is like this, abcd, right? So f1 is abcd, is summation m, these are mean terms, and f2 is these things. Now I use these two types of notation so that it will be more general for you to understand from one single example. Okay, here I have given in terms of summation m, and here I have given in terms of mean term addition only, right? SOP form directly. So in in this PAL implementation, what you have to do is remember one thing: while implementing any Boolean expression using PAL or PLA, we must write the given expression in the simplified version. Okay, simplified or minimized SOP form for PAL or PLA. While for implementing any Boolean expression using ROM, we need standard SOP form, right? Standard SOP. Okay, so that means if it is not in standard form, we have to write in standard form. And standard form means if we have 4 variables or 4 input variables, then mean terms must have all the 4 variables or 4 input variables in it. Okay, variables in it. This is the standard SOP form. But for PAL or PLA, we need simplified or minimized. That means we need to solve the given expression to get the standard form, right? Now here if you see, the expression given is this one in terms of this first f1 is this. F1 is given in terms of summation m, and f2 is given in terms of abcd only, right? So to solve this or to minimize this, we will use k map. See, this I can solve directly, but to simplify this we need k map. So we will use a k map, and in this k map, since 4 input variables are there, so 16 cells will be there, right? So let me draw this. So here we have a K map with 16 cells, and these are the cell numbers 0, 1, 2, 3. It is like this. Then comes 4, 5, 6, 7, and these cell numbers also represent mean term number, right? Okay, 7, and then 8 starts here, 8, 9, it is 10, 11, 12, 13, 14 and 15. Okay, and this is nothing but 0, 0, 0, 1, 1, 1, 1, 0. Here it is 0, 0, 0, 1, 1, 1, 1, 0. Now what we have to do? We have to write 1 for the given mean terms. Okay, and if mean terms are not given, we have to skip that, or we have to write 0. So here cell number 1 is there. 1 will be 1 is 1, then cell number 2 is 1, and this 1 means these mean terms are present, right? So mean term 1 is present, mean term 2 is present, Min terms 4 is there, 5 is there, 6, then 8, 10, 12 and 14. These are the min terms. Now we will simplify it, and to simplify what we will do the pairing. So if you see the pairing, this 4 will make a pair, this 2 will make a pair, correct? Then this 2 will make another pair, this 2, but there is no need to make a pair of these two, because we will have a pair of 4 like this. Yeah, see, this 2 and this 2. So a pair of 4 I will get from here, and we will have one more pair of 4 from here. These two elements paired with these two elements. Here if you see, this is the something which is not paired before this, right? So I can include this. So we have 4 pairs. If you see, pair number 1, pair number 2, from here I will have third pair, and from here I will have fourth pair. Now if you see, pair number 1 will give you C is 1 and D is 0. So from 1 I will have CD bar. From 2 I will have, if you see, A is 0 for both the elements, and C is 0, D is 0. A 0, C 0, D 0. That means it is nothing but A bar, C bar, D. From pair number 3 we will have, pair number 3 is this one. So for pair number 3, B is common. Okay, B is common, and if you see from these two, from here and here, if you see, then D bar is common because D equals to 0. So it will give you B D bar, and from fourth group we will have, if you see from this, A as common, so A is there, and from this 4 we will have D bar only, right? So A D bar. That means the given expression F1 is nothing but, it is like AD bar plus BD bar plus CD bar plus A bar, C bar, D. Okay. So this is the, simplified function F1. Okay. Now let me see, can we do something for function F2? Okay, so function F2 is given like this. Now there are two ways to solve function F2. We can use Boolean simplification also, as well as we can use K-map method also to get the simplified version of function F2. And I will show you both the way. And first I will focus on Boolean function simplification. So if you see Boolean function simplification method, then it is nothing but, I will take from this and this, B bar C bar or B dash C dash common. So it will be A dash plus A, and plus it is nothing but A dash B C D dash, right? And you know A plus A dash is nothing but 1. So this will give you B dash C dash plus A dash B C D dash, right? Remember this, after simplification I got something like this, B dash C dash plus A dash B C D dash. Okay. So this is my function F2. Now I will solve this using K-map. So to solve it or simplify this using K-map, what we have to do? We have to check number of input variables, and number of input variables here are 4, A, B, C, D. So we will make a K map which has 16 elements in it or 16 cells in it. So let me draw that first. Okay, now let me enter the data. So if you see here, the first term is a dash b dash c. Now if you see here, this 0 0 means it is nothing but a dash b dash, and this whole line is nothing but a dash b dash. Okay, similarly this whole line is nothing but ab, and if you see here, this whole line is for here. If you see, c is 0, d is 1, so this whole line is c bar d. Similarly this whole line is c d bar. So this is the way how we identify entries in K map. Now let me enter the entries. So first is a dash b dash c dash. So see, from here I will have a dash b dash, this whole thing is a dash b dash, and where is c dash? C dash means c complement, so c is equal to 0 in this whole line, and in this whole column it is c equals to 0. So point of intersection is these two, that means these 2 points will be representing a dash b dash c. So I will write 1 there. So to represent a dash b dash c dash in K map, I can use this thing. It is that, right? Then comes a dash b c dash. Now if you see, it is a dash b. This whole line is a dash b. Then I need c d dash. C dash is c d dash is this whole line, and only one point of intersection is there. So here I will write 1. Okay. So let me do that. Next is a b dash c dash. So where is a b dash? A b dash is this whole line. A equals to 0, b equals a equals to 1, b equals to 0. So this whole line is a b dash, and if you see, this whole line is c dash, right? And point of intersection is these two only. So 1 will come here. So let me do that also. So here comes 1. Now I will do the pairing. So if you see, these two and these two will make a pair of 4 element, and this is isolated, and it is nothing but a dash b c d dash only. And from this pair what we will have, let me see what is common. B dash is common, so b bar, and here c dash is common. If you see, c is 0, c is 0 for both, so c dash is common. So what I got from this, I got b dash c dash plus a dash b c d dash, and using that Boolean simplification also I got the same result. Okay, so now I can say the function given to me that should be implemented using PAL is this thing only, right? Now I am going to implement the given function using PAL. Okay, so I have already simplified, and after simplification I get f1 like this and f2 like this, right? And since we have 4 input variables, so we need 4 input buffer a b c d, and this will give us a bar, b bar, c bar, d and d bar. Now one more thing that is important here is it is PAL. Okay, so programmable and plus fixed OR. Now since AND is programmable, we have option to choose the inputs to AND gate or program AND gate, right? So we have option to program AND gate as per our requirement, but OR gate is fixed. Hence here number of input to OR gate will be fixed. Whatever OR gates we are using, number of input will be fixed. So number of input is fixed. Okay. Now if you see here, one more thing that I told is to use OR gate, we can just see what are number of outputs for the given Boolean expression or Boolean function. And here if you see, we have two outputs, f1 and f2. So number of OR gates required will be 2. And now let me see number of inputs to the OR gate. So if you see for function f1, number of inputs are 1 2 3 4. So ORing of these 4 inputs will give you f1, right? So number of inputs here are 4, and here number of input to, that means what I want to say is number of input to OR gate to get f1, okay, it is 4. And now number of input to get f2 is, see, this is one term and this is other term. So here number of input to OR gate is 2 only, right? So number of input is fixed, and what we can do, say, then we will select maximum number of input as number of input to the OR gate, right? And here maximum number of input is 4, correct? So we can do one thing, that number of input to OR is equal to number of, you can say, maximum min term to the outputs, like which output has maximum number of min term, right? So here maximum number of min term is 4, if you see. Fine. So in this case what we will have here, number of, for this particular example, number of input to OR equals to 4, right? To OR gate equals to 4. And number of OR gates are 2. One OR gate for F1, one OR gate for F2. That means total input required for OR gate will be 8, and these inputs will come from programmable AND gate. That means we need total number of 8 programmable AND gate, right? So here if you see number of, that means number of programmable AND gate is equal to that number of inputs to OR gate multiplied by number of OR gates used. And this number of OR gates is nothing but number of outputs, like here it is F1 F2, so 2 outputs were there, right? So in this case what will happen, 4 multiplied by 2, which is 8. So 8 and programmable AND gate will be required. Now I have used this, I have drawn already 4 and 4, total 8 AND gates. These 4 will be for like you can say for function f1, you can say this will be for function f2, you can say, or like that, okay. Okay, so now what I will do, so now I need connections. So if you see for function f1, I need AD dash, BD dash, CD dash, and A dash, C dash, D. Okay, so I will draw it here as I have already written the functions. So function f is this, and see here 2 OR gates are there, 2 OR gates are there, right? And these OR gates, first 4 from here, and like 1 2 3 4 will be connected to this OR, 5 6 7 8 will be connected here, and it will be connected, okay. So connections are shown by cross, as I have already told in ROM. So this will give you F1, okay, and then 5 6 7 8. And one more thing that I must tell you is, it will not be cross, it will be dot, because they are not programmable connection, they are fixed connection. And since they are fixed connection, so they will be represented by dot and not cross, okay. So let me remove these cross things. Okay, so this f1 is, this is AD bar plus bd bar plus cd bar plus a bar c bar d bar. Okay, that means I will make dot here to represent they are fixed connection. Okay, and f2 is b bar c bar plus a bar b c d bar. Okay, so I will make dots here to show fixed connection. Now if you see here ad bar plus bd bar plus cd bar plus a bar c bar d bar, that means from here I must have a d bar, from here I must have b d bar, from here I must have c d bar, and from here I must have a bar c bar d bar. Okay, and if you see here, so f2 is, from here I will have f2 is b bar c bar, right? That means from here I must have b bar c bar, from here I must have a bar b c d bar. Now if you see these two, from here I can say it is nothing but plus 0 plus 0, right? So from here I must have 0, and from here also I must have 0, right? So let me show how to get that things. Now let me see, here I want a d bar. Okay, so a will be coming from here, a, and here is the d bar, so it is a d bar b d bar, then from here I will have b, from here I will have d bar, so it is b d bar. Now c d bar, where is c? This cross will give me c, and this will give me d bar. Then a bar c bar d bar, from here I will have a bar, from here I will have c bar, and from here I will have d bar. Because see, from these buffer lines I told you this is a, this is a bar, this is b, this is b bar, this is c, this is c bar, d and d bar, right? Now if from here what I want b bar c bar, so this is b bar and this one is c bar, this is a bar b c d bar, so a bar b c and d bar. Now here I want 0 and 0, so what I will do, we will put a cross inside these two AND gates, and we call this as fuse intact. And fuse intact means these all are connected. It is not like we are removing the connection, it is like we are connecting all the points. And see why it will return you 0. It is like ending of a bar, b bar, c bar, d bar. Okay, so if you see what is a bar, it is 0. So similarly a bar, b bar, c bar all return 0. So from AND gate 7 and gate 8 we will get 0 as output, right? And remember one thing, all the connections they are connected initially, and we remove the connections which are not required. So here connections are already there and we don't want to remove. Okay, it will return 0 by default, so we are not changing it, we are not doing any changes to these things, and it returns 0 only, right? Now so if you see here we have programmable and plus fixed OR, right? These OR are fixed, and we will get f1 as ad bar plus bd bar plus cd bar plus a bar c bar d bar, and f2 as b bar c bar plus a bar b c d bar. So this is how you can implement any boolean function or boolean expression using PAL-PLD. For any doubt, feel free to contact me. Thank you. And in next class, I will implement boolean expression or boolean function using PLA, which is programmable logic.